Hi, everyone. I'm Reed. Tonight I'll be giving a guest lecture about irreducible polynomials that factor modulo every prime. It will touch on some very beautiful ideas from number theory and algebra. Feel free to interrupt me with a question or comment at any time. If you have a question about anything, or if you think I'm going too fast or anything like that, feel free to interrupt me. But yeah, so let's get started. Okay, can everyone see my lecture? All right, so it will be, okay, great. So here's sort of an outline of what we'll be doing. First, I'll review some preliminaries on irreducible polynomials. Then I'll define the symmetry group of a polynomial, and we'll see how questions about the symmetry group can lead us to answer questions about the polynomials. And then we will state, but we won't prove, two deep theorems about these symmetry groups and polynomials. And then we'll come back to symmetry groups and use these theorems to give a classification of polynomials that factor modulo every prime. And also, while I'm presenting, it's I can't really view chat at the same time, so I guess if there's a question I did not see, could you let me know, Andrew?
Yeah, that's how we've done it in the past. If a person asks a question in chat, I will unmute myself and ask you.
All right, great, thanks. Okay. So first, let's define an irreducible polynomial in case you haven't seen that before. So p of x is a polynomial, is integer coefficients. There's the sum of powers of some variable x. And we'll say it's irreducible over the integers if it's impossible to factor p of x into two non-constant integer polynomials of degree less than n. So here are some examples of irreducible polynomials. 7x plus 12 is an example because since it has degree 1, it's already completely factored. Like, the only way to further factor it would be to have factors of degree 0, and in the definition it says those aren't allowed. Another example is x squared minus 91, because 91 is not a perfect square. It's impossible to factor this over the integers. You could think of this as, since this is a quadratic polynomial, the only way it could factor is as a product of two linear polynomials, but that's impossible because 91 is not a perfect square. Another example is 3x cubed plus 2. Similarly to x squared minus 91, if 3x cubed plus 2, there are a couple ways it could factor would be as a product of three linear polynomials or quadratic times a linear polynomial. Either way, it's going to have some linear polynomial, but this is impossible because this polynomial has no integer roots. Now my last example is x to the fourth plus 1. It can't have any linear factors, but this doesn't mean it couldn't have factor as a product of two quadratics. And so to exclude this possibility, we'll show you how we could do that on using a whiteboard. Can everyone see the whiteboard? Okay. So we have the polynomial x to the fourth plus 1. And we want to show it can't be a product of two quadratics. So if we have our two quadratics, they'll have x squared. Remember, we'll do a proof by contradiction. So we have x squared and then some other stuff in both of these quadratics, because that's what the leading terms have to be. They could also be negative x squared in both times. But if that's the case, we can multiply each factor by -1. And since we're multiplying both factors by -1, we're multiplying the whole polynomial by 1. So this doesn't really change anything. And then the constant terms, they have to multiply to 1. And since they're integers, that means they each have to be -1 or they each have to be +1. So we can fill in the constant terms of these quadratics. And then we can't use the same trick we did before, assuming that they're +1, because we already assumed that x squared was +1. And so let's say that the linear term of this is some ax, or some integer a. Now the linear term we get when we multiply these two polynomials together, it will be, or I guess an easier way to see this would be with the cubic term. So from here, and let's say this linear term is bx. So when we multiply these polynomials, the cubic terms will come from x squared and bx, and from x squared and ax, which means that the cubic term is a plus b times x cubed. And that means that a plus b has to be 0, since this polynomial has no cubic term. Which means that actually b is just negative a. And now we can look at the quadratic term of the product. The quadratic terms would be from x squared and the constant term in both polynomials. And we also get a quadratic term when we multiply both linear terms. So that means the quadratic term of this polynomial would be when we multiply everything out, it would be plus or minus x squared, and then plus or minus x squared, and those have to be the same sign. So that's a plus minus 2x squared. And then the linear terms, when we multiply them, they give a further minus a squared, x squared. That means we have to have plus minus 2 minus a squared equals 0. But the only number a that could possibly satisfy that are plus and minus the square root of 2. And those aren't integers, which means that a can't be an integer, so x to the 4th plus 1 is irreducible. And then in this lecture, part of what we'll be doing is learning about better ways than just bashing to show a polynomial is irreducible. So one of the first ways we'll do is Eisenstein's criterion. And this says that if p of x is a to the n x to the n plus dot 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 plus a1x plus a0 is an integer polynomial, and for some prime p divides every a coefficient except the leading coefficient, and also p squared doesn't divide the last coefficient, then p of x is irreducible over the integers. And one way we could use this is to show that if p is prime, then this polynomial is irreducible, where it's x to the p minus 1 and x to the p minus 2 just going down. And we can't apply Eisenstein's criterion directly to this polynomial, and so instead we're going to translate this polynomial and then apply Eisenstein's criterion to the translated version. And to do that, I'll go pull up the whiteboard again. So we're going to instead show that, so our polynomial is x to the p minus 1 where every power of x from p minus 1 to 0 occurs and all the coefficients are plus 1. Now, this is a geometric series in x, and so that means we can sum it, and using the formula for a geometric series, we get that this polynomial is equal to x to the p minus 1 over x minus 1. And so if we translate x by 1, i.e. let x equal y plus 1, then we'll see what we get when we plug y plus 1 into here. So this becomes this. And now we can expand the top using the binomial theorem. And the constant term, when we expand this, would be just a 1. And then minus 1 would be a 0. So that means the numerator has no constant term, which means that we can divide by y and we'll actually get a polynomial as our answer. So the binomial theorem says that what we'll get when we expand this, the first term would be y to the p minus 1, because when we get a y to the p term, then we divide by y. The next term is p choose 1 times y to the p minus 2, because the other thing is a 1, so we just decrease the power of y each time. And normally, in the regular binomial theorem, you'd have a p minus 1 here, but since we're dividing by y, we decrease by the power by 1. And the next term is p choose 2 times y to the p minus 3, and so on. And we keep on going until we get down to p choose p minus 1 times y, and then the last term is just a plus 1, or plus p choose, or this should be a p minus 2, and then the last term is p choose p minus 1, yes. Because of the binomial theorem, this term, p choose p minus 1, is where y comes from, and then we divide by y and we get that. So the binomial coefficient, p choose k, is p factorial over k factorial times p minus k factorial. And if p minus k and k are both smaller than p, since p is prime, this quotient will be divisible by p. So that means every term in this polynomial is divisible by p, which is part of Eisenstein's criterion, which is right here, that p has to divide all the coefficients except the first one, and the first one is just 1, so that work checks out as well. And the last coefficient, p choose p minus 1, is just p, which is not divisible by p squared. So Eisenstein's criterion says that this polynomial must be irreducible. Another way to prove polynomials are irreducible is to reduce the modulo p for p prime. And what this is that show that for some prime p, for any hypothetical factorization of p of x and this hypothetical factorization, they could never possibly have the same remainder when you divide them by p. When you're proving a polynomial is irreducible in any way, what you're showing is that for any hypothetical factorization, it and p of x will never be equal. This is a similar idea, but we're lessening the requirement equal to the requirement has the same remainder when divided by p. And so let's see an example of how this would work. Our polynomial, it will be 5x cubed plus 17x minus 93, and we'll reduce it modulo 2. So the first step is that we replace all the coefficients of p with the remainders after division by the prime small p. And when we do this, we get the polynomial x cubed plus x plus 1. And the one way to think of this is you could think of this as an integer polynomial, but this isn't the best way to think of this. Instead, try to consider this polynomial having coefficients as classes of remainders modulo p. So like, this coefficient isn't 1, but you could think of it as the equivalence class of all integers that have remainder 1 when divided by p. So like, this coefficient is 1, but it could also be p plus 1, or 2p plus 1, or negative p plus 1, and so on. So like, these are a little bit different from normal polynomials. But if this is confusing, it's not that harmful if you just think of them as integer polynomials. Since this is a cubic, no, and we can, to check that since this is a cubic, to prove it's irreducible, we can show it has no linear factors, which means it has no roots modulo 2. So that means that we just have to plug in all remainder classes modulo 2, which are just 0 corresponding to even numbers and 1 corresponding to odd numbers. If we plug in the 0 remainder class, we get the 1 remainder class. If we plug in the 1 remainder class, we get the 1 plus 1 plus 1 remainder class, which is again 1. So it's irreducible modulo 2. And this implies it's irreducible over the integers, because if p of x factored as f of x g of x, then p hat of x, which is the notation I'll be using for taking the modulo p reduction of p, then it would factor as f hat of x times g hat of x modulo 2, and that's impossible. So this is sort of the main idea of factoring polynomials modulo p. And we'll be seeing this again and again throughout my lecture. And we can actually use this idea to prove Eisenstein's criterion. In other words, like Eisenstein's criterion is just a special case of this idea. So let p of x equal an x to the n, blah, 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 a1x plus a0, where all of these are integers as usual. And suppose some prime p divides every coefficient except for an, and that p squared doesn't divide a0, like in Eisenstein's criterion. And we'll do a proof by contradiction and assume p of x could factor as f of x g of x, and we'll derive a contradiction from this. So let's reduce this equation, p of x equals f of x g of x modulo p. So by what we assumed about the coefficients, all of these coefficients except an are 0 modulo p. And also an is non-zero modulo p, because if f of x g of x were 0, this just wouldn't tell us anything. It would only tell us that p divided every coefficient, which we can just factor out that p, and it doesn't really tell us anything about reducibility. Because f of x g of x factors as a n hat x to the n modulo p, f of x and g of x, when we take them modulo p, they have to factor as b1 hat x to the c1 times b and b2 hat x to the c2 when we compute them modulo p, because their product has this form, and this is the only way their product could have that form. And because the g of x and f of x become like this when we take the modulo p, every coefficient except their leading coefficients is divisible by p. In particular, both of their constant terms are divisible by p. But that means when we take the product of their constant terms, we get something that's divisible by p squared, and that contradicts the fact that p squared doesn't divide the constant term of p of x. And so this is why Eisenstein's criterion is true. Are there any questions about the proof of this, or about any of what I've covered just far? Okay, if there are no questions, then we'll move on. So let's see an example where modulo p reduction actually fails to prove anything. So earlier we showed x to the 4th plus 1 is irreducible over the integers. Let's try to factor this polynomial modulo 5. This is a version of difference of squares. 1 is congruent to -4 mod 5. So as we saw, where when changing the coefficients by multiples of p doesn't really change anything in modulo p land, we can just replace x to the 4th plus 1 with x to the 4th minus 4. And then we can just factor that with difference of squares. X to the 4th is the square of x squared, and 4 is the square of 2. So this factors as x squared plus 2 times x squared minus 2 modulo 5. Now the way to check this, one way to check this is that when we actually compute this product, you get x squared times x squared, which is x to the 4th. For the constant term, we get 2 times -2, which is -4, which is 1, which checks out. And then for the last term, we get we get -2x squared plus 2x squared, which is just 0, just like in the difference of squares factorization. And this polynomial, even though it's irreducible over the integers, it did factor modulo 5. And later, we'll see that x to the 4th plus 1 always factors modulo p for any prime p. And in this case, factoring modulo p didn't help us at all. In this lecture, the main point is classifying all the cases where modulo p factorization doesn't prove anything. And to work with this, we're going to introduce the symmetry group of a polynomial, which is an important tool that pops up all the time in algebra and number theory. So I could just give you the formal definition, but that would be bad because the formal definition is unmotivated and not very interesting at first glance. So instead, through this example, I'll sort of show intuitively what we would want the symmetry group to be. So p of x is our integer polynomial as usual. It may or may not be irreducible. If p of x has degree d, it will have d roots in the complex plane counted with multiplicity. So like multiplicity just means when we factor p of x as a product of linear factors over the complex numbers, some roots factor might appear twice, and we count that root twice. And it's a theorem that every polynomial will factor completely over the complex numbers, but we won't prove this here. Intuitively, you can think of this polynomial symmetry group as all the ways we can scramble its roots in such a way that preserves some algebraic relationships. And one way of thinking about this is with the polynomial x squared plus x plus 1. And we know it's irreducible because of what we proved here about polynomials that are prime. This polynomial is just x squared plus x plus 1 if p is the prime 3. So its roots, they're the third roots of unity, -1 plus root -3 over 2, and -1 minus root -3 over 2. So you can compute that these are actually the roots of it, and to actually find these roots, you can think about this using some geometry. If we multiply p of x by x minus 1, we get the polynomial x cubed minus 1. And so that means that all the roots of this are also roots of x cubed minus 1. And so you can think about geometrically that the roots of this polynomial will be take the unit circle in the complex numbers and travel around it by 1/3. And then you can use some trigonometry to calculate what that root actually is. And there's an algebraic relationship between these roots. In particular, omega 1 squared, that would be 1/4 times -1 plus root -3 squared. That's 1/4 times 1 minus 2 root -3 minus 3, which is just omega 2. And so since there's an algebraic relationship between these roots, we ask for the symmetry group to preserve this relationship. What this means is that if sigma is an element of the symmetry group, and sigma, as it turns out, will be a function, we require that sigma of omega squared equals sigma of omega squared. Are there any questions about this or about the idea of preserving algebraic relationships at all? Okay, if there are no questions, then moving on. And so that's what we mean by preserving algebraic relationships. In general, if psi and omega are any roots of p of x, and sigma is a scrambling or a permutation of the roots, sorry?
A student is asking, what exactly is a symmetry group?
Okay, so a symmetry group, it's you can think of it as the number of ways to transform our polynomial p in a way that preserves some structure. Like, for example, in geometry, you can often talk about symmetries there, and there, like when you rotate a polygon, for example, you're preserving the structure of the polygon and just moving it. And this is sort of a similar idea of preserving structure, except structure is not something you can see. Instead, it's the answer to some algebraic equation. Does that make sense? Okay, so we aren't actually transforming the polynomial. Instead, what we're transforming is we're transforming its roots. So like if I can show you on the whiteboard an example, if some of the roots are, let's call them omega 1 and omega 2, one transformation we could have might be to swap omega 2 and omega 1. And when we do the swapping, we want to preserve all algebraic relationships between those two. It's like in the example where we had omega 1 squared equals omega 2 squared. For swapping them to be in the symmetry group, we would want, after we swap them, for this equation to still be true. And so, or sorry, there shouldn't be a square there. We want omega 1 squared equals omega 2. So for swapping these two to be in the symmetry group, we would need the equation omega 2 squared equals omega 1 to be true. And you can check that similarly to example 2.1, that also omega 2 squared equals omega 1. Does that help? Oh, so idea 1.4 is just a way to label them so that I can refer back to them. You're free to ignore that part. Any more questions? Okay, if there are no more questions, then, and by the way, thank you for the good questions. I thought both of your questions were very good. So we can, another question. So I'm not deducing from something that O of omega squared equals O of W squared. Instead, what I'm asking for this to be true. So like what I'm saying is, if this is true, then what can we say about O? Does that make sense? Okay, great. Thanks, Kavan, Doctor. So for back to idea 1.4. So different remainders when divided by p. When you divide integers by something, you can divide them with remainder, and this means they have different remainder. Like for example, I could divide 15 by the prime 7. 15 is 14 plus 1, and 14 is a multiple of 7. It's 2 times 7. So 15 is 2 times 7 plus 1. It's impossible to fit any copies of 7 into plus 1. So we say that 15 has remainder 2 when divided by 7. For another example, if we have 31 and divide it by 7, well, 31 is 28 plus 3. 28 is 7 times 4, and you can't fit any 7s into 3. So 31 has remainder 3 when you divide it by 7. In general, if I write a number as a multiple of 7 plus something smaller than 7, the thing that's smaller than 7 will be its remainder. That's what remainders are, and they have different remainders if they have different remainders. Does that help? Okay, if there are no more questions, moving on then.
I think you missed one question at the end.
Sorry, Andrew?
There's one more question at the end. Why does the polynomial end?
So we're not saying this about a specific polynomial and a specific factorization. We're saying that this is something we want to prove for some polynomial and a hypothetical factorization. Is that helpful? Okay. Okay, so now that we're more familiar with the idea of preserving an algebraic relationship, if psi and omega are any two roots of p of x, And sigma, it's a scrambling of the roots. By preserving algebraic relationships, what we want is that sigma of omega times psi equals sigma of omega times sigma of psi, and similarly for addition. And again, these equations, I'm not deriving these equations from something, but these equations are things I want to be true about something. However, there's a problem here. So it's not always the case that the product of roots of a polynomial will again be a root of that polynomial. Similarly, the sum might also not be a root of that polynomial. That means that we need to define these elements of the symmetry group as functions. We have to define them on some bigger set. In particular, we want, in order for the asking for these to be true, for that question to even make sense, we have to take the roots of a polynomial along with all possible sums and products you can get from those roots. Similarly in taking all possible sums and products is what I mean by generating here. And because every polynomial has a complex root, this will be a subset of C, the complex numbers. That's what this fancy C means. It's also useful to define elements of the symmetry group on all the rational numbers. And we'll see that it's useful to just have any element of the symmetry group just do nothing to rational numbers. It's like it fixes all rational Q. So in particular, elements of the symmetry group are maps from some subset of C into itself. Now we can give an actual definition. So for any complex numbers, Z1 through Zn, we'll write Q adjoined Z1 through Zn is a set of all sums, products, differences, and quotients you can get from the Zi and from the rational numbers. And you can think of this as the subset that the Zi generate over Q, and where Q is the rational numbers for that fancy Q. It stands for quotient. And making this definition, it makes it such that these requirements on sigma actually make sense. So since we're taking all possible sums, we can ask about sigma of a sum, and similarly for the product. And so we define, let P of x be an integer polynomial of degree n. Its complex roots are alpha 1 through alpha n. The symmetry group of P of x is the set of all functions sigma from this set, which is the set generated by the alpha I, to itself, so that satisfy all the requirements in this page. So we require sigma of a times b equals sigma of a times sigma of b. We need sigma of a plus b equals sigma of a plus sigma of b. And we need sigma of q equals q if q is a rational number. Does this definition make sense to everyone? Okay, if there are no questions, then I'll move on. So here we'll see why all these requirements are a good idea to impose on sigma. And again, you should keep in mind that all the equations I'm writing, at least here, they're not equations I'm deriving, but they're things I want to impose on sigma. It's like, if that makes sense. So let alpha be a root of P of x, and let sigma be an element of the symmetry group. Since alpha is a root of P of x, we know P of alpha equals 0. And we're going to apply sigma to this equation. So writing out P of x in general form as an alpha to the n, blah, 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 plus a1 alpha plus a0 equals 0. So we're going to apply sigma to this equation. So sigma of that must equal sigma of that. Now first I'm going to claim that sigma of 0 has to be 0. To show this, I'm going to show you on the whiteboard. So recall that we have sigma of a plus b equals sigma of a plus sigma of b. Now, let's set b equals 0. So I'll change both b's to zeros. Now this is just sigma of a, because a plus 0 is a. So that means we have a sigma of a on that side, and a sigma of a plus sigma of 0 on that side. So we can just subtract sigma of a from both sides, and we're left with sigma of 0 equals 0. Of course, we could also have said that just because 0 is a rational number, sigma of 0 equals 0. But like this sort of formal algebraic thing is a useful sort of reasoning to use. It's like even if we didn't know that sigma of q equals q were true for 0, it would have to be true for 0 because of this property 4. And the sort of manipulation I did to prove that, it might remind you of functional equation problems if you ever worked on those. So now we have the second equation. We can break up the sum into sigma of a n alpha to the n plus sigma of a sub n minus 1 alpha to the n minus 1, and so on, having sigma of a1 alpha and sigma of a0 equals 0. An alpha to the n is an times alpha times alpha times alpha, and so on. And so since sigma also preserves multiplication, we can break this up into sigma of an times sigma of alpha to the n. And similarly for all the other terms. We would get sigma of a sub n minus 1 times sigma of alpha to the power n minus 1. And so on, sigma of a1, sigma of alpha, plus sigma of a0. The a sub I are integers, and in particular they're rational numbers, which means sigma fixes them. So a sub n sigma of alpha to the n plus a sub n minus 1 sigma of alpha to the n minus 1, and so on down to a1 sigma of alpha plus a0 equals 0. But p of x, is just a sub n x to the n plus a sub n minus 1 x to the n minus 1, and so on. So what this equation says is just p of sigma of alpha equals 0. In other words, if alpha is a root of p of x, then so is sigma of alpha. And so that means the intuitive idea of permuting the roots of a polynomial, these sigma that obey this formal definition do permute the roots of the polynomial. So like this is why it's a good idea to have this definition at all. So to give you some examples, I already sort of showed this example with w omega 1 and omega 2. So the roots of p of x equal x squared plus x plus 1. They're omega 1 and omega 2. We saw earlier that they satisfy omega 1 squared equals omega 2, and omega 2 squared equals omega 1. Now remember what the set Q adjoined the Zi is. It's what we get if we take the rational numbers, and we take the Zi, and we take all sums, products, differences, and quotients. And so that means that for this example, that set is all sums, products, and differences and quotients that you can form with the rational numbers omega 1 and omega 2. So that means you would get things like 5 plus 71 omega 1 minus 3 omega 2 omega 1. And you would get all the things like this. But because of the properties of that sigma, it preserves addition and preserves multiplication. And similarly to the calculation we did here, that means that sigma applied to any one of these expressions will be determined by where it sends omega 1 and where it sends omega 2. So we're determining the values of an entire function just from two values. Does that make sense to everyone, how we determine the entire function from just two values? Okay, if there are no questions about that, then we can see that the symmetry group of this polynomial, x squared plus x plus 1, is 2 elements. So we can either swap omega 1 and swap omega 2. And since omega 1 squared equals omega 2, and omega 2 squared equals omega 1, this doesn't violate any algebraic relationships between these roots. And the other thing we can do is just do nothing. And the reason these are the only things is because omega 1 has to go to either omega 1 or omega 2, because it has to go to another root of x squared plus x plus 1. And these are both those maps. Another example is with the polynomial p of x equals x cubed minus 2. It has roots cube root of 2, omega 1 cube root of 2, where omega 1 is the same thing as before. And recall that omega 1 cubed equals 1. So when we plug omega 1 cube root 2 into this, omega 1 cubed is 1, and cube root 2 is 2, and then 2 minus 2 is 0. Similarly, omega 2 cube root 2 is the last root of this. However, an element of this symmetry group, it's not just determined by where it sends cube root of 2. Because, like, for example, sigma of omega 1 cube root of 2 equals sigma of omega 1 times sigma of cube root of 2. So to know where this goes, we also have to know where sigma of omega 1 goes. It's not enough to only know that. And I haven't rigorously shown that omega 1 is, quote, independent, quote, of these values. But, like, it should sort of intuitively make sense why omega 1 would have to be independent of the value we chose for this. However, the map sigma, it is determined by sigma of omega 1 and sigma of the cube root of 2. Because if we know cube root 2, where cube root 2 goes, and we know where omega 1 goes, since sigma preserves products, then we know where omega 1 cube root 2 goes. And since omega 2 squared equals omega 2 equals omega 1 squared, and sigma preserves products, then we would also know where omega 2 cube root 2 goes. And the images, and these three values, they do determine all of where sigma goes. Similarly to how knowing where omega 1 and omega 2 went determine the entire map sigma in example 2.1. Does this sort, and then, so sigma could be sigma of omega 1 is determined by sigma of omega 1 and by sigma of cube root 2. Sigma of cube root 2 has 3 possibilities. Cube root 2 could go to here, or to here. And sigma of omega 1 has to be omega 1 or omega 2. So that gives us 2 times 3 equals 6 possible choices for each of these values. They yield distinct elements of the symmetry group, and every element of the symmetry group arises from such a choice. Does this sort of reasoning make sense to everyone? Okay, if there are no questions about that, then continuing on. So notice that in the example with x squared plus x plus 1, the symmetry group size equaled the degree of p of x. But in example 2.3, it was bigger. However, p of x had degree 3, and the symmetry group had size 6, which is 3 factorial. And this is a very general fact, that the size of the symmetry group will have size at most d factorial, where d is the degree of p of x. And we're not able to prove this here, but this is true. And if the symmetry group size equals the degree, the p of x is said to be normal. Now, examples 2.1 and 2.3, they both have extremely pretty geometric interpretations. And to see them, I'm going to plot the roots of each polynomial in the complex plane, and behold, it is the Illuminati, as you can see here. The red circle is the unit circle. The red dot marked here is just 0, 1, or 1. The red dot marked here is omega 1, and the red dot marked here is omega 2. And then the vertices of the blue triangle are the cube root of 2 right here, the cube root of 2 times omega 1 here, and the cube root of 2 times omega 2 here. The points marked on the red circle are the roots of unity, the cube roots of unity. And so to sort of see what the symmetry group does to this picture is the symmetry group of x squared plus x plus 1. It either fixes both omega 2 and omega 1, or it swaps them. And if it swaps them, notice that they're complex conjugates since they're symmetric about the real axis. And so that means that swapping omega 1 and omega 2 is the map complex conjugation. And technically, it's complex conjugation restricted to this set, because this set is not all of the complex numbers, but this is a technical point that doesn't really matter. And then for x cubed minus 2, you can think of the symmetry group of the polynomial as the ways to rotate and reflect the blue triangle here. So as an example, let's say we have the map of that fixes omega 1 and sends the cube root of 2 to cube root of 2 times omega 1. So the cube root of 2 goes to cube root of 2 times omega 1. The cube root of 2 times omega 1, which is this point. Since omega 1 is fixed, then sigma preserves multiplication. Sigma sends the cube root of 2 times omega 1 to the cube root of 2 times omega 2. And similarly, the cube root of 2 times omega 2 goes to here. So this vertex goes here, that vertex goes there, that vertex goes there. It's a rotation of the triangle clockwise, or counterclockwise. Wait. Yes, counterclockwise by 120 degrees. Similarly, if we send cube root of 2 to omega 2 cube root 2 and fix omega 1 and omega 2, then that will be rotation of the triangle by 240 degrees. You would have this vertex going over there, that vertex sends over here, and this vertex goes over here. And so those are the three possible rotations of the triangle. And to get reflections, we look at where omega 1 and omega 2 go. So if we fix cube root 2 and swap omega 1 and omega 2, then we'll fix this vertex, which is cube root 2, and we'll swap these two vertices. So that element of the symmetry group is just reflecting the triangle about the real axis. So that means that we've identified this polynomial symmetry group with a set of symmetries of the equilateral triangle. So does this geometric interpretation make sense to everyone? It's very nice, I think. Sorry. Okay, if there are no more questions, then continuing to move on. So I don't think I have enough time to prove or show everything in my lecture, but I can at least state the main result of my lecture. So p of x is a polynomial of degree n as usual. Let's label its roots as alpha 1 through alpha n. So every element of the symmetry group, it will correspond to some permutation of the alpha I. There are n factorial possible permutations of the alpha I, but this might not be, like, we won't necessarily have every possible permutation as an element of the symmetry group. Like, for example, we couldn't, like, send the roots to we couldn't send the roots to other roots in any way we wanted. We have to preserve some algebraic structure, as we saw earlier, so there aren't n factorial. And this correspondence, where a map of a symmetry group will correspond to a permutation of the roots, it will be a one-to-one correspondence precisely when P is normal. And so one nice way to write these permutations is if sigma sends alpha 1 to alpha I1, then alpha I1 to alpha I2, and so on, eventually sending alpha IK back to 1, we can represent it like this. So starting at 1, then going to I1, going to I2, and so on up until IK, which goes back to 1. So we just, like, follow the permutation along, starting from 1. there might be some other blocks in this decomposition, and the other blocks, they will be for roots that 1 doesn't ever go to. Like, for example, I'll pull up the whiteboard again. We could have, if n equals 5, let's say, we could have cycle 1, 2, 3, and then 4, 5. And what this means is that this is the permutation of 1 through 5. It sends 1, and I can write it down in this form, like this. So this says 1 goes to 2, and then 2 goes to 3, and then 3 goes back to 1. And this other cycle says 4 goes to 5, and 5 goes back to 4. So it just swaps 4 and 5. And you can see how like the cycles are disjoint, and that you don't have any lines crossing from these 3 numbers over into these 2 numbers. But if one of these cycles, there are multiple cycles in the decomposition. If it has k numbers in its block, we'll call it a k cycle. Using this notation, the symmetry group of x squared plus x plus 1 is 1, and I'll use this notation for just the identity or the do-nothing map, and then 1, 2, which corresponded to swapping the 2 roots. And then the symmetry group, we say it's transitive if every alpha I will map to every other alpha j. So like some element of the symmetry group will send alpha I to alpha j for every possible I and j. So like everything gets sent to everything. This is not the same as a symmetry group being every permutation, because you don't need to have every permutation to be able to map everything to everything. But that's what this means. It's like transitive, anyone can go anywhere, basically. And so we have this theorem. If p of x is a polynomial with no repeated roots whose symmetry group is transitive, then it has to be irreducible. And so the upshot of this theorem is that the symmetry group, as we've seen, it's a finite combinatorial object. And this theorem is telling us that using a combinatorial property of this finite object, we can prove results about polynomials being reducible. So suppose for contradiction that the theorem is false. So symmetry group of p of x is transitive, but p of x does factor into factors as p of x equals f of x g of x. But these are not f and g are non-constant integer polynomials. Now recall from the calculation of this slide, the same sort of idea where we apply sigma to the whole polynomial and break it up term by term, then break it up into products. The same idea, it shows that the symmetry group, it will always send roots of f to other roots of f, and roots of g to other roots of g. And if p of x has no repeated roots, then the roots of f are different from the roots of g. But since the symmetry group must send roots of f again, and roots of g again, it's impossible for it to send any root of f to a root of g. But this is a contradiction, because then the symmetry group is no longer transitive. Like, some roots of f can't go to the roots of g. So it's false that anything can go anywhere, and so it's not transitive. Does the idea of this proof make sense to everyone? Okay, if there are no questions about that, then going on. Sorry. Okay. Okay, now I won't be able to state in detail on this part since my time is almost up. But here is another relation between the two symmetry groups. It's named after Dedekind and Kummer. And Dedekind and Kummer are the two scary-looking German dudes you see below. There's Dedekind on the left and Kummer on the right. And you cannot go far in number theory or algebra without encountering these guys' names over and over and over again. They were incredible number theorists, and so many things are named after them. But what we can do is this gives a relation between symmetry groups and factoring modulo p, the theorem they proved in the 1800s. So p of x is a normal polynomial, which means that symmetry group has the same size as its degree. And p is a prime which doesn't defy the discriminant of p of x. The discriminant, I'm not going to really say what it is, and you are fine if you just ignore what it is. But you can think of the discriminant as tracking when the polynomial has multiple roots. Like, for example, a discriminant of a quadratic polynomial is b squared minus 4ac. And we know that b squared minus 4ac equals 0 if and only if that quadratic polynomial has a double root. And there's a generalization of this idea of the discriminant to higher degree. But we can take p of x and factor it modulo p as f1 hat times f2 hat, and so on up through fk hat, where the hat just emphasizes that their polynomial is modulo p. And then the Dedekind-Kummer theorem, it's the symmetry group of p of x. It contains an element with cycle lengths d1, d2, up through dk, where di is the degree of fi. And to help with understanding this, I have an example for you. So using x to the fourth plus 1 again, we can take on faith that this polynomial has discriminant 2 to the 8th. And so this theorem, it applies for any odd prime p. So what this says is that recall modulo 5, we have the factorization into irreducibles, x to the fourth plus 1 equals x squared plus 2 times x squared minus 2, using difference of squares with 1 replaced with negative 4. And so that means that theorem 3.3, it says x to the fourth plus 1's symmetry group has an element that has cycle looks like this. And one way to see what this cycle does, I can show you on the whiteboard, is there are 4 elements, so 4. And what this theorem is saying about the symmetry group is that it has an element that acts like this on the roots. So the polynomial, p of x has 4 roots, and the symmetry group contains an element that does this to the roots. It swaps 2 of them and swaps the other 2. That's what this theorem says. Are there any questions about this theorem or my example of it? We won't be able to prove it here, but it's a very interesting result that I thought I might mention. Okay, so I'm going to skip some of the content of my lecture. Unfortunately, we're already over time and I want to finish soon. But there's another mathematician who is important to us called Chebatarov, and he is from Russia, and he is happy looking. You can see him sitting in his office working on stuff, not scary like the German guys here. But sort of the main takeaway from this presentation is using the Dedekind-Kummer and Chebatarov theorems, we can say precisely when modulo p reduction will fail to prove that a polynomial is irreducible. So let p of x be normal and irreducible having degree d. P of x is not irreducible modulo every prime p if and only if the cycle structure of a single d cycle does not appear in p of x's symmetry group. So like with x to the fourth plus 1, what this is saying is that a element of the symmetry group that looks like this, that's a 4 cycle. So like 1 goes to 2, then to 3, then to 4, and then back to 1. So it cycles back in 4 things. That's why it's called a 4 cycle. It's saying that this, if this does not appear in the symmetry group of x to the fourth plus 1, then x to the fourth plus 1 will factor modulo every prime p. And we're over time, and this is sort of all that I have for you guys. Are there any questions at all about any of the things I said, or any questions for me about math? Or about my school. I go to Princeton if you're curious about that. But that's basically all. Thank you.
Thank you so much. That was really good. I enjoyed it a lot.
Thanks, Andrew.
And as I said at the beginning of this, Reed is a very cool person with lots of interesting things to say. So if you guys have any questions about anything at all, feel free.
Yes, if any of you might have a question you might want to ask me later, I can put my email in the chat. Feel free to email me at readmj536@gmail.com. But I hope my lecture was interesting and that you learned something cool from it.
I think this is the second time in a row Jason has arrived after the lecture ended.
So lots of things besides math competitions. Like this question, like competitions are like very far from the only way to learn math. But I guess just find a topic you're interested in and take a class. I imagine if you emailed a professor at a college nearby, they would be more than happy to let you sit in on their class. Like perhaps maybe a college is offering a combinatorics class you're interested in, or a number theory class. You could even take like an intro analysis class would maybe be a good option for some of you. You can just get a textbook on a topic that interests you and learn from it that way. There are tons of math programs you can do, like Everraise, and there are also many other programs. I went to Canada USA Math Camp, and it is very dear to my heart that you can go to these programs and learn lots of interesting non-competition math there. But yeah. So I used Overleaf to make my slides. And in Overleaf, I used a package called Beamer. And to use Beamer, when at the top of your Overleaf document, when you have document class, you'll write, instead of document class equals article, you'll write document class equals Beamer. And Beamer will have a pre-chosen template that will let you do these nice slides. It was Beamer Madrid. Yes, I did go very fast at the end. I wanted to at least get to state the main result before I was too over on time. Sorry for going fast. And if you have any questions about the material at the end, feel free to ask them. Okay, if you could tell your ninth grade self one thing knowing what you know right now, what would it be? So in ninth grade, I had not started learning math at all. I only really started studying math in 10th grade when I took some AOPS classes. They're number theory and counting and probability classes. And so I would just tell my ninth grade self to take AOPS classes, and then I would have been interested in math a year earlier than when I actually started being interested in math. Send you the slides. Or I guess, Andrew, I could email the slides to you, and then you could share them with all Everraise people?
Yeah, that sounds good.
Okay, cool. I will compile a PDF and send that to Andrew, and he can send it to you guys in a bit. Worst waste of time in high school. I'm tempted to say college apps, but I feel like this would not be a good answer because college apps are like actually important. But probably worst waste of, okay, oh, I know. So after 10th grade, when I take on these wonderful and exciting AOPS classes, I was unable to take AOPS calculus in 11th grade because it conflicted with a weekly activity I had. And so instead, my parents enrolled me in this other calculus class. And this calculus class, which I eventually dropped out of and just studied AOPS calculus's book on my own, was the biggest waste of the time in high school. Question about math camp. So at math camp, there are new classes every week. It's 5 weeks long, and you can take up to 4 classes every week, and even more in the 5th week, because in the 5th week, 1 hour reserved for studying is changed into an extra hour of classes. And so there are too many classes for me to remember or name, but some of my favorites were a class on Galois theory, which relates to some of the ideas I talked about today. In particular, the object I called a symmetry group, what's really called is a Galois group, and you'll encounter these if you study number theory or abstract algebra. But Galois theory was one of my favorite math camp classes. I also really enjoyed a class about hyperbolic geometry, which is a way of doing geometry where through any point and given a point and a line that does not pass through that point, there are infinitely many parallel lines to the given line through that point. So a very weird and interesting land of geometry. Another very good class was a class on Hamiltonian cycles and graphs. But these are just some of favorites off the top of my head. The dorm experience. So at math camp, this year it's online, but usually it would be at a college, and you live in the college dorms. So dorm equivalent of a college dorm. Math camp is usually at colleges where the dorms are pretty nice. So like in both my years, we had AC in the dorms. We had lots of spacious lounges to congregate and do activities and stuff. But the social experience was definitely the best part of math camp. And everyone I met was super interesting and inspiring and fun to be around. And math camp really provided a wonderful community of fellow math lovers, which I did not have in my hometown. And this is why math camp is important to me, I think. More questions. So starting contest math later than the average student. So this was me. I started doing math in 10th grade. And even then, I didn't really do competitions so much as just learning math. Like after taking counting and probability and number theory from AOPS, I encountered Evan Chin's napkin before I could. Oh, sad about Ross. I encountered the napkin in lots of interesting group theory and higher math before I could be seduced by competitions. And I thought the material in napkin was more interesting to me than competitions, so I just studied that rather than competitions. But so I guess that doesn't answer your question, sorry. But I think if you're starting competition math later, certainly don't do only competition math, because if you're starting later, then like it becomes less important, I guess. And I guess just do the best you can at competitions, regardless of when you start doing them, but only if they're fun. You should not do competitions if they are not fun. So textbook for high school learning about groups. I think probably Michael Arton's algebra book might be a good place to start. You could also try reading the first couple chapters of Evan Chin's Napkin. Another good but more challenging algebra book is one by Dummett and Foote. Those are some pretty good resources about group theory and other algebra topics. Oh, starting to learn analysis. So my favorite analysis book is a set of lecture notes by a guy named Charles Pugh, P-U-G-H. His lectures, contain a tremendous amount of exercises, and analysis is often presented like very formally. But I found this Pugh resource made analysis very intuitive, and it also contains, in addition to analysis, some neat diversions. Like he describes a very fascinating way to visualize four-dimensional space. You're welcome, Ezra. So life at Princeton. So I really love Princeton. I found that like it was great to be able to meet people with many diverse interests, math and non-math, and I liked that a lot. Like at Princeton, or you would find people interested in things from literature to foreign languages to humanities, to math and science as well. And this was very appealing since I enjoy literature and philosophy and things like that. I guess like life in general, this is like a very broad question. Like every school, Princeton has like little quirks that characterize its life. Like we have a thing called late meal, where the campus center is open from 3 to 5, and you can get second lunch, basically. Our math building, it's referred to as the Tower of Doom, sort of, because it is 13 stories tall. And people have compared it to Mount Doom from Lord of the Rings. We have a math common room, which is incredibly nice. It's on the 3rd floor of the math building, but like in every weekday at 4 p.m., like they will have free cookies and tea for everyone. And so all the math professors and math grad students will come to that. And it's a really great way to socialize with math people and meet people and have fun.
Thank you so much, Reed. I think if that's all for now, we're gonna have to cut you off here.
Yeah, it's almost 9 o'clock, so but
Yeah.
thank you, Andrew. I enjoyed giving this lecture and chatting with everyone. You're welcome, Jet.